Today I'd like to talk to you about tangent planes. And so to start off, I'm just going to define a parametric function in 3 dimensions. So if we have some function of t, r of t, which is equal to g of t in the I direction plus h of t in the j direction plus k of t in the k direction. If this is a smooth curve, on the level surface f of x, y, z is equal to c, then we have that f of g of t, h of t, k of t is equal to c. And so if we have that f of g of t, h of t, k of t is equal to c, then we could take the derivative of both sides of that equation with respect to t. And on the one side, I'd just get the derivative of that function with respect to t, so d dt of f of g of t, h of t, k of t. And on the other side, I would get the derivative with respect to t of the constant c. In other words, on the left-hand side, I'm going to use the chain rule. And the chain rule tells me how I would take this derivative is I'd take the partial of f with respect to x times the derivative of g with respect to t plus the partial of f with respect to y times the derivative of h with respect to t plus the partial of f with respect to z times the derivative of k with respect to t. And on the other side, the derivative of constant, I just get 0. Okay. Another way of writing that, so I've got the partial with respect to x, the partial with respect to y, the partial with respect to z, and then I have dg dt, dh dt, dk dt, and those are multiplied together. Another way that I could write that is the following. I have that the gradient of f dot dr dt is equal to 0. Okay? What is this saying to me? Well, what this is saying is that at a point p sub 0, all the velocity vectors dr dt are orthogonal to the gradient of f. Okay. So what this is saying is that if I have some level curve, let me just draw some level curve. Let's say that this is our level curve, and I have a point P0 on that level curve. Then I have some velocity vector, I could call it. But another way of thinking about it is it's kind of like a tangent vector. So if I had some tangent vector, typically we call a vector like that dr dt. so if this is dr dt as a vector, then I know that the gradient vector is at a right angle to that velocity vector. So any velocity vector I draw in this thing is normal or at a right angle to the gradient vector at that point. And that's going to be important for us later. So let's remember that velocity vectors and gradient vectors are orthogonal. Okay, so now we need a definition. So definition. The tangent plane at a point p sub 0, which is x0, y0, z0, on the level surface f of x, y, z is equal to c of a differentiable function f is the plane through p sub 0 normal to the gradient of f evaluated at that point p sub 0. Okay. And also the normal line of the surface at p sub 0 is the line through P0 parallel to the gradient of f evaluated at P0. Okay, so we have two things here we're talking about. First one is the tangent plane of a surface, and the second one is the normal line at a point on a surface. Okay, so let me draw a picture of each of these first, just so we can kind of get a feel for what we're talking about. So let's say that I have some surface. Let's draw a paraboloid. Okay, and let's take a point on that paraboloid. Now, it's not really enough anymore to talk about a tangent line at that point. That doesn't make any sense. What we talk about now is we would talk about a tangent plane at that point, because there isn't just one tangent line. There are many tangent lines depending on the direction you want to go from that point. So in fact, there are infinite tangent lines, but they all belong to one common plane. So that plane at that point, planes can be hard to draw, but we have a plane that is tangent to that point. We call that plane the tangent plane. Now, we will also get a line that's coming straight out of that point that's normal to that plane. And that line that is normal to this plane, it's at a right angle to the plane, is called the normal line. Okay? And what we're seeing is that this tangent plane is going to be orthogonal to our gradient. Okay, that's going to help us. So now let me write a few more things about our tangent plane and our normal line. So here's a tangent plane. For the function f of x, y, z is equal to c at a point P0, which is x0, y0, z0. Okay, so the way that I would find a tangent plane is the following formula. So I'd take the partial of f with respect to x and evaluate it at the point P0, and then multiply that by x minus x0, plus the partial of y at the point P0 times y minus y0, plus the partial of f with respect to z evaluated at P0 times z minus z0, and all of that would be equal to 0. Okay, and so this is how we will in general find the tangent plane for a function of 3 variables, or in this case we might consider this a level surface. And so here is the equation for our tangent plane at a given point x0, y0, z0. Okay, I also need the same thing for a normal line. So if I want a normal line, to the function f of x, y, z is equal to c at a point P0, which is x0, y0, z0. Remember that lines in 3 dimensions are described parametrically. So the way that I would write this is that x is going to be x0 plus the partial of the partial derivative with respect to x evaluated at p sub 0 times t. Y will be y0 plus the partial with respect to y at p0 times t, and then z will be z sub 0 plus the partial with respect to z at p0 times t. Now notice that x0, y0, z0, that's just my point, and then the partial at p0, the partial of y at p0, the partial of z at p0, that is in some respect my I guess you could kind of think of that as the normal vector itself, right? So we have some normal vector. What do we call that normal vector? Typically we call that the gradient. But this is the gradient evaluated at P0. Those are the components that go in to my line equation. Okay, so I've got a point and I've got a normal vector that are giving me my parametric line. Okay, so let's do an example. So now I have equations for both a tangent plane and a normal line. Now let's see what we can do with that. So here's an example for you. Find the equation. For the tangent plane and normal line at the point P sub 0, which is the point 1, 1, 1, for the curve x squared plus y squared plus z squared is equal to 3. Okay, so first of all, we look at this curve and we say, what kind of a curve is that? Well, that's a sphere centered at the origin. Its radius is square root of 3. And so we kind of know what we're dealing with here, and we're asking, what's the tangent plane at the point 1, 1, 1? Well, now we know how to find the tangent plane. We just have to find the partials, and the partials will give us our equation for the tangent plane. So first thing that I really need is I need to know what's the partial with respect to x of this function. And the partial with respect to x is just 2x. Then I could ask, well, what's the partial with respect to y? It's just 2y. And what's the partial with respect to z? It's just 2z. Okay. Now I could say, well, what if I plugged in the point P0? So what's the partial with respect to x evaluated at P sub 0? Well, that would just be 2, because x is equal to 1. The partial of y evaluated at P0 is also going to be 2. And the partial with respect to z at P0 is also going to be 2. Okay, so I plug this into my plane equation, and I get the partial of x at P0, which is 2, times x minus x0. x0 is 1. So I get 2 times x minus 1, plus 2 times y minus 1, plus 2 times z minus 1 is equal to 0. And now if I wanted to do some simplification of this thing, I could. And what would I get? I'd get 2x plus 2y plus 2z is equal to, well, what would it be? It would be minus 2, minus 2, minus 2 is minus 6. But if I move that to the other side, it would be 6. So this is the equation of my tangent plane. Okay, that's kind of interesting. And now I'd want to find also the normal line. The normal line, we also have an equation for, but that equation for the normal line, I'm going to just erase real quick here. So the normal line, I have a parametric curve. So I want to write it parametrically. And so the normal line, I already know what the partials are, 2, 2, and 2. And so if I want to find the normal line, I want x is equal to x0, which is 1, plus the partial with respect to x evaluated at P0, which we said was 2t. Y is going to be, well, 1 plus 2t. And z is going to be 1 plus the partial with respect to z evaluated at P0 was 2t. So this would be the parametric form of the normal line to that curve f at the point P0. Okay, very good. Now, what if, for this specific example, we're taking the tangent plane and the normal line to a level surface. In other words, you have f of x, y, z equals a constant. We could just as easily have expressed that as something more like a surface that's defined as a function. So what if you had a tangent plane to the surface z is equal to f of xy? So you have z is equal to a function of two variables. Well, another way of writing that z is equal to f of xy is that f of xy minus z is equal to 0. And now we could just think of this as a level surface, where on the left we have a function of x, y, and z, and on the right we have a constant 0. So now we could just take the partials in terms of this new function of x, y, and z. So the partial here with respect to x of the left side is just going to be the partial with respect to x of f of xy. The partial with respect to y, in this case, is just the partial with respect to y of xy. And the partial with respect to z, in this case, if this is the left side, that's my function, the partial with respect to z is just -1. Okay, so now if we have a z equals f of xy, then the way that we could write the tangent plane is the following. So the tangent plane is similar. It's the partial with respect to x evaluated at x0, y0 times x minus x0 plus partial with respect to y of x0, y0 times y minus y0 plus, well, now the partial with respect to z, I know that. It's -1. So instead of putting a minus right there, I could put, instead of putting a plus right here, let's change that to a -1 times z minus z0, and that's all equal to 0. So now we have this nice formula. Okay, so the only difference if I'm dealing with an actual surface function instead of a level surface, which are two different things, then I can just treat that surface as a level surface by moving everything to the left side and writing it as f of xy minus z equals 0, and then I can find the equation of my tangent plane. And the only difference is if all you have is a z, the partial with respect to z is just -1. We just plug that in and everything's the same. Okay, so that's how you would go about a tangent plane if you're dealing with a specific surface. So maybe let's do a quick example like that. So example, let's find a tangent plane to the curve z is equal to e to the power negative x squared plus y squared at the point P0, which is 0, 0, 1, and at the point 1, 0, 1 over e. Okay. So how do we go about finding these tangent planes? Well, now we know that we need to find a partial with respect to x. We need a partial with respect to y. We don't really need the partial with respect to z because this is a z equals a function of x and y. So let's find this partial with respect to x and this partial with respect to y. Okay, so the partial with respect to x, we have e to a power, so the derivative of e to a power is just e to that power, times the derivative of the power with respect to x. but the derivative of that power with respect to x is going to be minus 2x. Okay, and what's the partial with respect to y? Very similar. E to the minus x squared plus y squared times negative 2y. Okay. Now we need to evaluate those at the point. So right now we're working with the point 0, 0, 1. Well, if I'm working with the point 0, 0, 1 at P0, then what do I get over here when I plug in 0, 0, 1? Well, if x is 0, then f, the partial of f with respect to x, is just 0 because I have this x right here. And if y is 0, I also get 0. So if I'm plugging this into my tangent plane formula, I get 0 times x minus x0, which is 0, plus 0 times y minus y0, which is 0, minus 1 times z minus z sub 0, which is 1, equals 0. So this guy just goes away, this guy just goes away, and I'm left with negative z plus 1 equals 0, or if you wanted to kind of rewrite that, that's z equals 1. And that's the equation of the tangent plane, is just z equals 1. Okay, we did it for one point. Let's try a point that's maybe a little more complicated than 0, 0, 1, where everything becomes 0. So let's look at the point 1, 0, 1 over e. Okay, so let me erase a few things real quick here. So if we change the point to the point 0, 1, 1 over e, how does that change things? So this isn't 0 anymore, this isn't 0 anymore. What would they be? So if x is 1, then I get e to the negative, 1 squared, which is 1, plus 0 squared, times negative 2 times 1. Okay, for the second piece, I still have this y is going to be 0, so I get 0. And that's all. So what is this? So this is e to the negative 1 times negative 2. So it's minus 2 divided by e. All right? So now I've got my partial with respect to x, I've got my partial with respect to y, so I'm ready to fill in what is the actual tangent plane. So I get the partial with respect to x, evaluated at the point, negative 2 over e, times x minus x0, which is 1, plus f sub y, which is 0, times y minus y1, which is 0, minus 1 times z minus z sub 0, which is 1 over e, is equal to 0. So now if I wanted to, I could expand this a little bit, and I get minus 2 over e times x plus 2 over e. That all goes away, and I get minus z plus 1 over e. Okay, is equal to 0. And now if I wanted to clean this up a little bit, I suppose I get negative 2 over e x minus z is equal to, well, what would this be? 2e over e plus 1 over e is 3 over e. If I throw that on the other side, it's minus 3 over e. And then if I wanted to, I could multiply both sides by negative 1 and make all these positive. So I get 2 over ex plus z equals 3 over e would be my tangent plane. Sound good? Okay, let's do one more example. So an example, the surfaces first of all, f of xyz is equal to x squared plus y squared minus 2 equals 0. And g of x, y, z, which is equal to x plus z minus 4 equals 0, meet in an ellipse. Let's call it E. Okay, so before I go about writing any more of the problem, let's just take a look at this. So first of all, what is this curve? That curve is x squared plus y squared. If I move the 2 to the other side, is equal to 2. So that's actually a cylinder. So if I were to draw my x, y, z axis here, and I were to go out square root of 2, and I draw a circle here, well, that circle would, the z is free to do whatever it wants, so that would go up in this direction, up in this direction, and also down. And so this would create this cylinder, correct? Then I have this additional function x plus z equals 4. So x plus z equals 4 is a plane that would cut through, let's see. So if x is 0, z must be 4. So it cuts through at an angle up here. And then it's level with y. So we kind of have this. Ooh, that was not good. So we kind of have this plane that goes. Intersecting with this cylinder. So let me try to draw it over here a little bit better. So I have a cylinder. Of course, it goes up infinitely far, and then it's cut through by a plane. And so where it intersects would look something like this. And so it would intersect that plane at some ellipse. Okay, so that ellipse where they intersect is what I'll call E. So that's the ellipse E. Now notice that the ellipse E is a part of the cylinder, and it is a part of the plane. It's both, correct? Okay, so now here's the question. Let's find a parametric equation for the tangent line to E at the point 1, 1, 3. Okay, so let me write that down. So let's find parametric equations for the line tangent to E at the point P0 is equal to 1, 1, 3. Now, we don't know a lot about that specific tangent line. let me draw again here. So we've got this nice cylinder. We've got a plane that's cutting through that cylinder. And we've got an ellipse being formed by that cut. And now we've got a point on that ellipse. And we want to find an equation for the tangent line to that ellipse at that point. Okay, so this is obviously a line in 3 dimensions, so it's going to be a parametric line. But here's, if you go back to the very beginning of the lecture, I said something. And I said that a tangent line, or a vector that is, or a tangent vector, if you like, is always normal to the gradient. Now, this is 2 curves, and each of those curves has a gradient at that point. And so each of those gradients is going to be orthogonal to that tangent line. Okay, so what was the first curve? Well, it was x squared plus y squared minus 2 equals 0. So I might say, okay, what is the gradient? This was f. So I might ask, what's the gradient of f? Well, it's the partial with respect to x, which is 2x in the I direction, plus the partial with respect to y, which is 2y in the j direction, plus the partial with respect to z, which is 0 in the k direction. If I want to write that down, 0 in the k direction. Okay, so that's the gradient with respect to f, but it's at a specific point. The point is 113. So I could plug that in, and I get that the gradient of f evaluated at p0 would be 2i plus 2j, and that's it. 2i plus 2j. So I get some gradient. Now, that gradient I know is normal to that tangent line. So which curve is this, by the way? This is the cylinder. So this thing lives on the cylinder, and we're going to, and the gradient is normal to it. So maybe this points like inward or something. Okay? Now, but it is normal to that tangent line. Now let's look at g of xyz. And g of xyz was x plus z minus 4 equals 0. So let's think about the gradient of g. Well, with respect to x, I'd get 1i. With respect to y, I'd get plus 0j. And with respect to z, I'd get plus 1k. And if I plug in my points, there are no x, y's, or z's left. So I could just write this as I plus k. And I plus k is also normal to this thing. It's normal in a different direction, but maybe I'd draw it this way. And it's also normal to that tangent line. Now, notice that these two are not parallel to each other. So if I have something that's normal to this one and it's normal to this one, those two lie in a common plane. And that plane has a normal vector. That normal vector must be on the tangent line, or pointing in the same direction as the tangent line. So if I can just find that normal vector, that will help me to create this tangent line. So what I want to do is use these two gradients to find this normal vector. Well, how do you find a normal vector using two vectors? I cross those two vectors, and it gives me a vector that's normal to both of them. So I want to cross the gradient of f and the gradient of g. Let's do it. So I want the gradient of f cross the gradient of g. Both of them, of course, evaluated at the point P0. So that's going to be the determinant of I, j, k, and then 2, 2, 0, and 1, 0, 1. Okay, let's see what we get. First, I do the positive ones. I get 2i. Then I get j times 0 times 1, which is 0. Then I get k times 0 times 2, which is 0. So I just get 2i minus, now I go the other way, I get 2k. Then I get j times 2 times 1. Here, let me go back here. J times 2 times 1, which is 2j. And then I get I times 0, which is 0. Okay, so let's write this in the correct order. So I get 2i minus 2j minus 2k. And this would be a normal vector to that ellipse. Now I need to use a normal vector to get a normal line. Well, a line is going to be x equals, I used the point. What was the point again in this problem? It was the point 1, 1, 3. So I use the point, that's my x0, so 1 plus, now this is my normal vector, so I use 2t. Y is equal to y0, which is 1, plus negative 2t. And z is equal to z0, which is 3, plus negative 2t. And that will give me my tangent line to the intersection of those two curves. So I was able to use information about the gradients of each to find a normal vector to the curve. And then I was able to use that normal vector to create a parametric line that is tangent to the curve. Make sense? Okay, I hope so. Time for some homework.